So webinar is live.
Great.
Lucas, I'm not seeing the.
Yeah, it's recording.
Yeah, thank you.
Great. Welcome everyone. We're gonna get started in a few minutes.
Nobody else on yet?
We are live, so let's go ahead and I think get going.
Yeah, totally. Well, I'm excited to get started, and we will wait for more folks to join on. This is another episode of Ask Mayfield Anything, and we're really excited to have all of you joining today. Just a reminder, we do have a Q&A box for you to submit any of your questions that you would like our panelists to answer today regarding Megawatt Design considerations. You can also put your questions in the chat while our speakers are talking. So we are going to get started today. So hi, my name is Christy Drutman. I am the content marketing coordinator at Mayfield Renewables, and I will be moderating today's conversation. And I am joined today by Ryan Mayfield, who is the founder and CEO of Mayfield Renewables. Ryan has been working in the renewable energy field since 1999 and founded Mayfield Renewables in 2007. His career has blended technical expertise with an affinity for writing and education. Ryan holds a limited renewable energy technician license in Oregon and is an Oregon Solar Energy Industries Association board member.
Actually, I need to update that. My board membership just finished up just about a month ago, so I probably need to update my bio there. But
on that.
we'll make note of that. Welcome everybody, and thanks, Christy. Really excited to have another episode here and chat with you all.
Great, and now I'm excited to introduce today's special guest, Randy Batchelor from SolRepl. Randy has over 14 years of experience working in the solar industry, specializing in engineering and construction of solar and energy storage systems. He has led the design and engineering of over 50 megawatts of large commercial and industrial solar projects, from preliminary design to commercial operation, and has been involved in various stages of project development, interconnection, permitting, and construction for many more. Randy is a licensed professional electrical engineer and is the CEO and founder of SolRepl. Thank you for joining us today, Randy.
Yeah, happy to be here.
Great. Well, for today's topic, we are going to be talking about megawatt scale PV system design, specifically looking at optimization for two common system constraints: inverter load ratios and ground coverage ratios. This talk will be covering subtopics that will be addressed in our upcoming HeatSpring course on Megawatt Design that launches May 3rd on HeatSpring. So to start off our talk, before we dive into system design optimization, I wanted to start off by asking Randy, could you define to the audience how system constraints are defined?
Yeah, sure. So I think, so we're going to be talking about optimizing systems for ground coverage ratio and inverter loading ratio, and some of the design considerations that influence what the final answer is coming out of that optimization exercise. And one of the best ways to think about optimization and the factors that drive your optimal system design are system constraints. And so when we're designing a system, we pretty much always are looking for the largest system size that we can within a certain set of constraints, because larger system sizes typically mean lower cost per watt. Every project has a lot of fixed costs, such as design and engineering and project management. And so the bigger your project, or the more kilowatt hours or the more kilowatts you're able to put out, generally the lower cost per watt it's going to be, and the better the economics of the system, to a point. And the question is, what is that point? Where's the point where you have diminishing returns? And that's largely determined by what is constraining that size of the system, what's limiting you from going larger. And there's two main types of constraints, and we'll talk about a couple different variations here. But the two main constraints are the AC system size, the interconnection size, usually like the ampacity of, for a behind the meter system, the ampacity of the existing switchgear, for example. And the other main constraint is the amount of space available to install your solar, or kind of more, another way of thinking about this is, DC size constrained versus AC size constrained. So those are kind of the two main constraints, and within that, there's some nuance and some subcategories. There's load constraints, there's some structural constraints, but those two buckets are kind of going to be some of the biggest drivers of what your optimal system design is going to look like.
Awesome. Well, thank you for setting the context of today's conversation. To start off, we're going to have Ryan kick it off by talking about space constraints.
Well, yeah, and so as Randy was saying, the constraints are there, and so I mean, love to get some of your input and everything here too, Randy. But yeah, talking about space constrained, and what we're looking at here is a rooftop system. And so rooftop systems inherently being space constrained, you only have so much roof area that you can cover. And so in a situation like this, we talked about optimizing for with ground coverage ratio, GCR, ground coverage ratio. And so we're talking about there the amount of array you have compared to the amount of area that you have to cover it. And so if you are going to really pack that in and get a higher GCR, then this, that's one of the constraints that we're working around. And part of this, when you're thinking about roof-mounted systems, when we were all learning system design, and when we're learning about PV systems, you want to have your PV rate and optimal angle pointing directly at the sun, all those kinds of things. But then when you run the calculations and you run the math, in a lot of ways, having a lower tilt is going to produce more kilowatt hours. And ultimately, that's really what people are after, are kilowatt hours being generated from the system. And so I think looking at the space constraints, helping to minimize the LCOE is a pretty big thing. And so, I guess, Randy, just curious on what you're seeing out there on your designs. I know you do a lot of ground mounts and things like that, but in terms of ground coverage ratio, with respect to, since we're talking about rooftops first and foremost.
Yeah, on rooftops, it's definitely a lot denser in general than on ground mounts, and that does kind of get to the point of, a lot of times we are very much more space constrained, and also I think we've got another slide on structural constraints. There's major disadvantages with going with a higher tilt on a roof, because you have increased structural loading, higher wind loading with higher tilts on a roof. And so by getting down to that lower tilt, you're reducing the structural loads, and so you're able to fit a lot more. And also, because we don't have foundations and that we're really trying to reduce the foundations. We've got attachments and ballasts usually. It's kind of what leads us to, the real common types of, ballasted rooftop systems for large rooftops. So, your 5-degree and your 10-degree tilt, from the likes of Panel Claw and Unirac and Iron Ridge, there's good reasons why we've gone there as an industry and gravitated towards, those few, those options for rooftop racking systems, especially the large flat roofs where we're using ballasted systems. You're pretty much exclusively seeing, that those 5 and 10-degree tilt systems used across the markets across the country.
Yep.
That's what I'm seeing. That's what you're seeing too, right?
Oh yeah, absolutely. Yeah, and even getting into these, east-west type systems where you're maximizing the roof coverage, but at those very, very low angles.
Yeah, exactly. And so then, once we know that, okay, 5 or 10 degrees is going to be, we're probably going to want one of those options. Then you're basically looking at, okay, are we 5-degree or is it 10-degree? And then what row spacing do we want to go with? And I think that's where, even on rooftop systems, sometimes occasionally you'll be more interconnection constrained. And so, if you're already up at a higher loading ratio, if you're already up to a higher loading ratio and there's still available space on the roof, that's when you start spacing out the system more. And, like if you look at some of the options from, say, Panel Claw or Iron Ridge, right? You typically have like, there'd be a 10-degree system with an option for a 10-inch row spacing, a 14-inch row spacing, and a 17-inch row spacing, something like that. I have to go pull that up to have that off the top. And at that point, it's really easy it's nice that you actually have kind of a limited number of options compared to ground mount, where you kind of do more or less anything you want. Because then you have a limited number of options that you can look at and analyze and see, what's going to be the best way to go here. And with tools like Helioscope and Aurora, you can iterate on those designs pretty rapidly and see what the impact is going to be to your total kilowatt hour production, especially if you've got a fixed AC system size, which often you would.
Yeah, and so I was just going to say, speaking of you mentioned ground mount systems being able to do pretty much whatever you want. And so, here, very often you're still going to be space constrained. Not always. I mean, sometimes you have all the available land that you need. But yeah, and so in this case, we see this is actually a single axis tracking system. And so the spacing becomes a function of the tilt angle and location on Earth, how far apart you need to spread those out. And so that becomes now just a new function of your ground cover. It's a way of looking at your ground coverage ratio, and what those constraints are.
Yeah, exactly. Yeah, and it's interesting. I actually had, probably for the first time ever, a project that was completely unspace constrained. It was a 500 kilowatt project. It was limited by load, and it was a greenhouse out in the desert in Utah, and there was just unlimited land, unlimited flat land, and my client, the contractor, was like, well, just space them out so that there's no inner row shading. And I kind of had to go through a surprising amount of explanation to explain to him that you cannot, in fact, have a situation where there is no inter-row shading. We can just go bigger and bigger, and even that site that had seemingly unlimited space now has a limit to it, right? You can just keep spacing out the system to reduce more and more of your shading. At some point, and typically, it's really around that. That 9 to 3 shading window. If you do the math on a 9 to 3 row to row shading, that's where once you get outside of that 9 to 3 on December 21st, that's where you start seeing like, okay, there's really minimal shading at that point already. So kind of spacing out your rows any further than that has very little return. And in fact, you just start spending more money on wire because you're having longer runs because your array is so much bigger. That's pretty rare. So even in like on a project that's completely unspace constrained, you know, there's just some practicalities of, you know, we don't want to take up more space than we need to. Maybe the landowner could do something else with this land. Maybe they can't. You know, maybe it really is, you know, like this desert, and they just have gobs of room. But that's really rare. And so if you take that as kind of a maximum of like completely on space constraint, and then you just start shrinking down, and you get to a point where now your row to row shading is increasing, and you're looking at how can I increase my system size while reducing the row to row shading.
Are you seeing, and I'm not sure that I have an answer for this, I'm just curious on, you know, any standard ground coverage ratios? I mean, are you guys starting with a standard value and iterating from there when you're looking at, you know, new designs?
Yeah, it's a good question. It's funny because I think maybe we talked about this briefly in our one of our prep sessions. But you know, for the longest time over the last, you know, say 5 or 10 years, I actually haven't been thinking about, especially fixed tilt systems, in terms of ground coverage ratio very much. I had been thinking of fixed tilt systems mostly just in terms of row to row spacing, either row to row on center or the, you know, like in helioscope, you measure the distance between the rows from the back, to the front of the next. And then when you start analyzing, you know, when you start looking at a bunch of different module options, and I think part of the reason that I was mostly thinking that for a long time we were kind of locked into a pretty uniform form factor, which was, you know, your 1 meter by 2 meter module, whether that was, you know, a 350, 370, or 400 watt. Now, all of a sudden, just in the last year, we've seen this big jump up to this much larger form factor, you know, which is like the 530s and 580s, or even like the 450s and 470s. And when you start looking at different size modules, that's when you really have to shift, and you're comparing one module to another module that's completely different size. And you definitely have to start thinking about ground coverage ratio instead of just row spacing. So, and it goes for trackers as well, that we think about row spacing a lot just in terms of the feet between the rows. But I think for a long time, people have, for whatever reason, always talked about ground coverage ratio more with trackers. So I think historically it has been, and it still continues to be, a good rule of thumb with trackers that you're going to want to be between, you know, a 0.3 to a 0.4 ground coverage ratio. And pretty consistently across the country and in lots of different markets, I rarely see it going outside of that range. Even, you know, when we do the analysis and we go down to 0.25 and up to 0.45 or 0.5, the right answer or the optimized design still often falls, you know, in that, you know, and really in that, you know, 0.35 is a good starting point for most trackers.
We do have a quick question in the chat that I would love for you to add on to this. It's a question from Adam Bagnall. The question asks, what drives the decision of using a panel claw ballasted system facing south versus the panel claw dual tilt east-west? I assume that's what
Adam. So Adam's on my team. I got to admit. He's trying to stump me there. It's a good question. It's a hard one because they're very different. But generally, the east-west is even higher density. So that's where you're going to want to. It's higher density, so meaning even higher ground coverage ratio than, you know, a 5-degree system it can be, a lot of the 5-degree systems, there's a lot of feedback from the field that with really tight row spacing on a 5-degree system, it actually makes the installation really difficult. If you have to go back and redo wiring, there's not enough room to walk between the rows of modules to get in there and do that work. So that's a challenge. And the east-west, even though it's higher density and you have the panels facing both directions, will actually have a little more space there. The other thing that the east-west orientation does is that because you're picking up, because you're picking up from like the east facing, you get more production in the morning, and then the west facing, you have more production in the afternoon. And so kind of on net, it kind of balances out the curve, and instead of your bell-shaped curve on your energy production, you get wider shoulders on it. You kind of get that more production in the morning and the afternoon. So if you can split that onto an inverter, so if you can have them for example, if you use the core ones and you put the east facing on one MPPT and the west facing on another MPPT, you can actually reduce the clipping on the inverter while increasing the loading, because you're reducing the peak in the middle of the day and having more energy production on the shoulders. So that's another benefit. So there's a few different things there, and if there's anybody else on the or Ryan, if there's anybody else on the chat has any other ideas, that I'm all
yeah.
ears.
Well, one of the things I always think about, and so I switched the slide back just to show that east-west, just for everybody to see, have a visual of what we're talking about. Installation is one thing that always comes up in my mind too, Randy. How the ease of installation, and then with module level power electronics, that's another part of it. So if you're doing something with DC optimizers, your layout isn't nearly as critical. But if you are not using, if you're just using straight rapid shutdown kits or something like that, then all of a sudden you have to start really mapping this out, be thinking about the installation crew, how they're stringing these modules together, those kinds of things. So that's always one of the things that comes up in my mind when we start talking about these. And we've had projects where module changed, between design and installation, and it changed the stringing, and it just all of a sudden the east-west wasn't as straightforward as it once was. So it's great in the sense of packing it in, but then there's all these ancillary things that you need to be considering.
Yeah, and if Adam was on here too, he could emphasize the challenges of stringing an east-west system, because we just went through that and trying to do exactly what I was talking about, where you're segregating the east and the west on separate MPPTs, but trying to split the loading between so that you've got half east, half west on each inverter. It's to really take advantage of all that is really challenging.
Right.
And the stringing is tougher on these than normal systems, where you just go back and forth, because you have to skip every other row when you're stringing it. So, yeah, it can be really challenging for sure.
I really love this other question. It's by James Orenstein. James asks, are rooftop single axis trackers practical?
I've done one in 20 years.
Yeah, the short answer is no. I really, and there's a lot of good reasons for that. I'd rather not go into that too much. But there's a lot of, it's mainly for structural reasons. That it's not practical. And I've seen there's some product where they're like east-west tilted, like doing this, that I saw recently, and it's also your attachments are really challenging. You're having a lot of attachments. It's just not really worth the bang for the buck. And keep it simple. 5-10 degree tilt ballasted rooftop systems work great. They're profitable. They get good returns in most markets. There's not a whole lot of reason to add the complication.
So good segue though into kind of another one of the constraints that we're going to talk about here today, of structural capacity restraints. And I think that's people are probably pretty well aware of rooftop system specifically is what we're talking about. You're putting ballast, you're putting an array down, you're putting racking down, you're putting ballast pans down, or ballast in the ballast pans. And so you're adding, in some cases, a significant amount of weight. And not all buildings are going to be able to support that. And so the idea, again, kind of getting back to some earlier things that we were saying is, you can see this picture, very low tilt array. Tilt angle keeps the wind loading down, really helps distribute that weight. And so that's always another constraint, and it can directly affect the size of your system. So yeah, I'm not sure, Randy, if you have a whole lot more to add to that one.
Yeah, no, I think that's right. And for one, like we talked about earlier, for rooftops, it really just makes going with higher tilt systems is just not practical. And a lot of jurisdictions also have height restrictions in general. For zoning purposes as well as structural reasons. And so that drives the 5 and 10 degree. Occasionally we see 15-degree tilt systems, but not really. But then, also, if you're limited by, for example, the amount of weight that you can put on a roof, and you're talking about ballasted systems, that can do one of two things. One is just limits the amount of solar that you can put on the roof. So it might be about a ton of space up there, but you can't use it because you're limited by the amount of weight that you can put on the roof. The other thing that it does is, even if you there's the trade-off between ballast and attachments in most ballasted, rooftop ballasted systems. They're hybrid, right? And so in general, the more weight that you put on the roof, the more you can reduce the attachments to a point. If there's size requirements, often you always need some attachments. And then, but if you wanted to reduce the weight, you can pull the ballast off and do more attachments, but that becomes uneconomical because attachments are very expensive. Usually, $120 to $180 to it per attachment is kind of a typical sort of all-in cost when you're doing this kind of value engineering. And so you get to a point where you start adding a lot of cost if you add attachments. And so then the question is, like, does it make sense to go bigger, because or does it make sense to if you are weight constrained, does it make sense to go with a larger DC system size, at a much higher cost per watt? And so so generally that will kind of lead you towards if you've got lots of extra space on the roof, it'll lead you towards smaller ground coverage ratio, more spread out array, and usually lower inverter loading ratios. So, less DC size to a higher AC size, because, you want to reduce the clipping, and there's no reason to push it, especially if there's plenty of AC interconnection capacity. So that's typically what we see coming out of, rooftops that are structurally constrained. I was trying to think if that kind of applies to ground mounts at all too, but not really. It's more geotechnical than structural. You do see some structural constraints on ground mounts where you have really high snow loading, in some areas of northern New York or Maine or Minnesota or something like that, where you have high snow loads. You end up getting a lot more foundations per rack. You might not, trackers may not even be an option, but that's rarely the case. Usually it's more just an issue of just, if you've got loose ground and you need to have, more screws or deeper piles or something like that, those can drive design.
Similar situation though. Your geotechnical issues and kind of parallel with your structural on a building.
Yeah, exactly. Yeah, it's similar stuff, but there's less of things that apply on like a site. You can't be limited by a site, and it's more just, okay, we have more costs for our foundation, right. And then maybe it makes less sense to put in more DC system size, to really crank up the loading ratio if your cost per watt is already high. You want
Mhm.
a higher specific yield.
Right. So we'll get into inverter loading ratio in just a sec, but let's talk a little bit about the AC interconnection constraints. And so this is one, we're starting to see more and more, especially where we live, here in Oregon. We're starting to see this where the lines are, the utilities are getting, well, they're claiming they're getting saturated. I don't know if saturated is quite the right word for it, but lots and lots of solar getting production put on their lines with low usage, low consumption in a lot of these areas. So, we're seeing these larger farms out in rural areas, and they're just capacity constrained. And so we're starting to see this more and more, where just your interconnection, restraints are becoming part of it. And so that it will play directly into inverter loading ratio, which we'll talk about. But yeah, I mean, this is an issue, and this is what's going to come up. You should be catching this in interconnection when you're doing your interconnection applications, is really where it's coming up. And so, yeah, I guess, Randy, are you seeing? I'm presuming you're seeing a lot of the same things. I know you do work.
Yeah.
A lot of our work is really focused on the West Coast, and I know you do some more on the East Coast. And so I was just curious on that East Coast perspective too.
Yeah, absolutely. Yeah, I mean, I think that it depends a lot on the types of projects you're talking about. I think when it comes to large ground mount front of the meter projects, kind of two distinct buckets. And most of what we work on is the distributed generation, distributed distribution level interconnection. So 12 to 15 kV, and most of those are typically capped at 5 megawatts AC, which is a FERC limit, and that kind of rolls down into a lot of the state programs, like in the Northeast, but also in California. You see that 5 megawatt cap for applies to some of the transmission fees and things in Cal ISO as well. And so that's one of we see that 5 megawatt cap a lot across the country for distributed interconnection. And then when you get above that into the bigger utility scale stuff, which we don't do as much of, it really the interconnection is more just driven by the size of the transmission lines and so forth that are available in the interconnection. But even the sub 5 megawatt, we're also seeing a lot of you go and do the study, or you go do a preliminary analysis, and you can only interconnect 3 megawatts AC. And if you've got a huge site with lots of space available, big ag sites like what you've got on the screen here, that's going to drive really high loading ratios. And that's that's what we, because you kind of get to that point where you reach the practical limit of ground coverage ratio, right? You're like, okay, we have plenty of space. It doesn't make any sense to go, like, let's say on a fixed tilt, it doesn't really make any sense to go lower than, like, say 0.4 or something on a fixed tilt, or 0.3 on a tracker, something like that, because your wire costs start going up, and all this kind of stuff. You also are paying for, a lot of times even if the grading or the civil work is minimal, you're still talking more civil site work. If you're covering more land, you're going to have to reseed. There's a fence going around. There's a road going through. All of those factors kind of limit the minimum ground coverage ratio that makes sense. And then if you're AC limited, then you just push right up against, and if you still have space, you just push right up against the limits of the inverter. And so a lot of systems now we're seeing going in at the 1.5, right up at a lot of, and we can get more into this in a second, but we see more and more systems going in at the limits of what the inverter can handle for loading ratios. Yeah.
Right. Yeah, so let's talk about that. That's one of the big things, and I think that's one of the, when when we were talking about this, the inverter load ratios was one of the things. And so I think it's interesting, talk a little bit about the history. When you and I got started, I remember 1.25 being kind of the magic number for inverter loading ratio. So, 125% more DC or solar capacity than what the AC the inverter could produce. And in a lot of ways, that was, you would never see clipping or power limitation from the inverter at a 1.25 to 1 ratio. Maybe if, probably in the, single digit or, dozen hours a year or something like that, maybe, just when you consider all the losses associated with it, but very, very little amount of time that you would do that.
Like, less than 2% clipping losses,
right.
Usually if you're 1.25, so it doesn't make any sense to go lower than that, right?
Right.
Yeah.
And that just being a function of, the physics of the whole system. You have at least that much loss before you even get to the inverter. So, and the inverter is only so efficient, so you can't, even if you did a 1-to-1 ratio, which I remember actually doing in way back when PV modules
there were people 10, 15 years ago who thought that was the thing.
Right. Well, when you're paying $4.50, $5 a watt just for the solar, not for the system, just for the PV, people didn't like to see any of those kilowatt hours go away. So,
Right.
But as PV, and so I think that was a big function of it, PV, and I get that question a lot, is, why were we doing that? PV prices were so expensive. Now we are, sub 50 cents a watt. I mean, there's.
Yeah, and labor and balance of materials and everything else too,
right.
was a lot, right?
Sure.
And so you don't, you pay a premium, so you really want to eke out, you want to really bump up the specific yield. You want as many kilowatt hours per kilowatt of solar installed, right?
Right. And so bumping up your inverter load ratio is going to achieve that. And so we're seeing, 1.35 is pretty much not minimum, but that's kind of the starting point for designs really anymore. And you just mentioned 1.5. And so, yeah, so I guess maybe we could talk through this a little bit, just in terms of putting in the higher loading ratio will ultimately equate to more kilowatt hours, is really what it comes down to. And kind of back to your point you were just talking about of, if you're AC constrained, if you're interconnection constrained, if you can only do 5 megawatts of AC output, then you would want to, they're not saying your kilowatt hour restrained, your power constrained, not energy constrained. And so you really want to, and energy is what we're getting paid for ultimately anyway. And so you're gonna push those limits. And I know you and I were talking recently, and you're seeing some pretty aggressive pushing on those as well.
Yeah. Before we jump into that, the really aggressive pushing, and I think, we can get to the kind of what's limiting the inverter loading ratio in a minute. But I think, when you're in the kind of this normal range, we're seeing the same thing. 1.3 or 1.35 is a good starting point now, and it depends where you are and what the other constraints are on a system. But there still are a lot of systems where that makes sense, especially where you have lower cost of power and more land available. Like in the West, you're going to want to have higher specific yield, higher kilowatt hours per kilowatt, and you're still going to want low clipping, because the energy's worth less. And so you want to make sure that in order to get the best return on investment, that you're not paying too much for those kilowatt hours. And so if you're installing more than you need and your kilowatt hours per kilowatts low, if your specific yield is lower, which happens as your loading ratio goes up, then you're paying more money for your install, because you're paying for more kilowatts to go in the ground, and all of the, for the modules and the racking and all of the balance of system costs associated with that. So there are systems that are, where you're not space constrained, and you've got, you've got low cost of power where you're going to have lower loading ratios, and especially if you don't have as much AC constraints. But yeah, a lot of scenarios we are seeing people, with these really high loading ratios, and the kind of general rule of thumb, and pretty much across the board with all different types of inverters, you're getting a general feedback that 1.5 is sort of a limit on inverters, and that's still kind of a reality. But what we're also starting to see is that, because across the markets and across the industry, there is a push for higher loading ratios, that the inverter manufacturers are getting much more sophisticated in how they talk about this topic. So, I mean, I think that's maybe a good segue to say, okay, like, what does limit the inverters, right?
Yeah.
So what's kind of been your historical experience with, dealing with inverter manufacturers, and what's the maximum loading ratio you can put on it?
The most I'm starting to see more and more, but the thing that we've always had them hang their hat on is, whatever it says on the spec, which 1.5 to 1 has been recently kind of the upper end. Starting to see some, though, talk about 2 to 1 even on their spec sheets, and we haven't had an opportunity to go 2 to 1 on any of our projects, but I'm really curious and would love to talk more about kind of how what the justification there is, especially with the inverter manufacturers, because that seems, you were just saying, 1.5 is kind of a working limit, and that's been pretty much what our approach has been on our system designs.
Yeah. I mean, my experience, and what I've noticed, like, in terms of like the manufacturer spec sheets and how they state the limits, historically, a lot they've had a maximum DC power input, or a maximum loading ratio, same on the spec sheet. I'm starting to just not see that on the spec sheets anymore at all. So most of them will now state a maximum current input, which to me is a much more valid way to state that. But even there, I think a lot of times when they're pressed, the inverter manufacturers will be like, well, it's not really a hard limit, you could go higher. And really recently, they're starting to push those numbers way up, because the reality of how the inverters operate is that they limit the input current, by moving maximum power point tracking, the tracking point, and just moving where they're operating on the curve, so that the current that the inverter sees is low, and so you're never really at risk of exceeding the input current on the inverters. From a practical perspective, really what you're doing is just loading the inverter up for more hours of the year, right? And having the inverter operating at full throttle, at full capacity, which just stresses the components of the inverters more. And so that's really like it's more kind of a longer term look at, like, okay, now you have these electronic components that are under full load, fully stressed, running hot for more hours a year. And so how does that affect the 10, 20-year outlook for how long this inverter is going to last, and the inverter warranty? And that's where it starts becoming an issue for the inverter manufacturers, and they're starting to look at it in a more sophisticated way. And I had a really great conversation with a guy from SMA that actually came out of the posting on LinkedIn for this session here. And SMA is looking at a maximum loading hours for the year as how they limit that.
Oh, really?
Now.
Okay.
Yeah. So the the maximum input current, they still have that on the spec sheet, but it's really high. It's up in the 1.8 to 2 kind of range, the maximum short circuit, and that's almost just a function of what the size of the cables that you can fit on the inverter inputs, really, as much as anything. And that's actually well, I don't know if we want to dive into the weeds on that now, but there's a new code section that you and I talked about, Ryan,
Right.
in 2020, where you can actually limit the current input on your inverters. If you've got a combiner box, you can limit the size of your DC conductors to, to the inverter input limit. So whatever that the inverter is capping the input of the DC input at, rather than sizing those conductors for the output of your solar. You know that it's never going to go more than the rated input of the inverter, so you can size your conductors down.
Right.
But yeah, so they do have a limit on the current input, but it's really high. But instead, they're basically running a production model and saying it's like, I think it was like 2,400 hours a year or something that the inverter can't for SMA anyway. And I might have that number wrong. If the guy's on, you can chat and correct me. And so I thought that was an interesting and a much more sophisticated way to look at it than the
That is interesting. So are they? I guess the question would be then, what modeling are we relying on at that point?
Right. So I mean, I think at that point probably is a conversation. And I'm willing to bet that the answer would probably, well, you can use whatever model you want, but at the end of the day, what matters is how it's going to operate in the field, right?
Right.
And so if you exceed that number, whatever it is, call it 2,400 hours a year, where you're operating at 100% capacity, then their warranty is no good, right?
Sure.
So you decide, right?
I guess it's kind of like with open circuit voltage.
Right.
It's up to you to decide what that number is, but the inverter is going to know what it is and it's going to record it. So if you hit 1501, the inverter is going to know it, and you just went out of spec.
Yeah.
This is a clarifying question. Is loading ratio different than AC ratio? Just for people who may not know if those terms are different.
No, it's loading ratio is DC to AC ratio. It's just the rated DC power at STC to the rated AC power output of the inverter. Yep. Yeah,
sorry, that was
good question.
Should have put that up there earlier. Sorry.
Where was I?
So now you were just talking about at least SMA's approach, and I'd be curious to see if other manufacturers are doing the same, just in terms of number of hours. And so is that something that's, I hadn't heard that, and so is that something that they are now implementing, or is this they're looking into it? Do you know?
No, I think they're now implementing it. Yeah.
Okay.
Yeah. SMA is now implementing that. And yeah, I wouldn't be surprised if other manufacturers start going the same route, because it just kind of it seems like it's the right answer. But like Selectria is now states on their spec sheets that they'll get up to like a 2 or even higher, I think. There's a few different manufacturers that do that. And I guess before I jump into the DC coupled battery scenario for why that happens, it's also worth mentioning the hyperclipping issue, just to make sure that folks are aware of that. So if you're not aware, we can post that link to that Paul Grana article on hyperclipping.
Yeah.
You can Google the solar hyperclipping. There's a great article by Paul Grana from Helioscope that's on Solar Power World blog. It explains it really well. But essentially, when you get into these high loading ratios, if you also are really up against the limit of the string size, it's hard to describe without pictures. Probably should have thrown a slide in about it. But basically what happens is you can sort of miss the inverter operating MPPT operating window if the voltage is too high. And the result is that instead of just clipping the power to the inverter output, the inverter can't actually put out any power during that period. And that's because it's trying to find the maximum voltage in order to keep the current with it, under the rated input current of the inverter. And in order for that to happen, it just completely misses the inverter operating window and sends it to 0. So anybody, you can look into hyperclipping. It's something to be aware of. You can see it in helioscope if you look at the 8760s, or PVSys actually gives you like an error message and says you have X number of hours per year where this occurred. I can't remember the exact language. And some hyperclipping does in these high loading ratios, high VOC scenarios. Some is acceptable and some happens, and you can do that 12 hours a year or something. But you get into some scenarios where it happens a lot, and it's like majorly detrimental. You all of a sudden you go from, oh, okay, you start like going up and up, and you get like 1.5, 1.6, 1.7, and at some point you're like, you go from, oh, I've got clipping of 5%, 6%, 7%, 20%, and there's like all of a sudden there's this major jump, and your clipping just goes out of whack. And it's because of that hyper clipping scenario that happens where you miss the voltage window. So something for everybody to be aware of.
Yeah, and it's the way I was thinking about it when I looked at that is it's almost the opposite of if your strings are too short and your voltage is falling out of the bottom side of that operating window. Your strings are so long, exactly, and you have so much power, you're actually falling outside of it on the other side of that window. So it's kind of this, again, years ago never would have been even heard of or considered, but because of this combination of long strings and high loading ratios, we're missing you have the potential of missing that window, the operating window of the inverter.
Yeah, and there is the code section, the NEC code section where you can model the VOC in production modeling software or in SAM to increase your string length. You can do that, but the hyperclipping becomes an issue at a much lower loading ratio if you do that, you try to exceed the normal kind of string voltage calc that you do by doing the modeling.
Amazing.
Yeah.
We do need to move on to the final questions in our Q&A box, even though you all are covering such amazing topics. But we do want to get to other folks' questions. So I wanted to ask you, maybe we could just, cover 2 or 3 of these questions in the short time we have left. But one of the questions that was asked by Drew is, do any per acre system capacity limits exist for ground mount systems? For example, 200 kilowatts per acre.
Yeah, I think the short answer is no. I mean, I think there's rules of thumb, and that 200 kilowatts per acre is a great rule of thumb. If somebody asks me, hey, how much can we fit on a site? I'll say, yeah, 5 acres a megawatt is a great rule of thumb. But no, the only limits, especially on a ground mount, would be like impervious surface or typically environmental restrictions or zoning restrictions on covered acres, and typically solar panels aren't typically considered covered for like impervious surface calculations. It's just like the number of foundations and the amount of road, and then a lot of places have kind of areas of maximum disturbed acres, so that's really the only primary driver of that.
Yeah. And the zone, there's other zoning that we've seen a lot too, and just on allowable number of acres that you can take if it's considered farmland, for example. They consider taking that out of production, that kind of stuff. So, but yeah, those.
And our other last question is, how does using dual axis trackers impact ground cover ratios?
Yeah, I don't have very much experience with dual axis trackers. I would imagine that you're going to have much lower coverage rate.
Yeah, and actually I didn't get to make it on the site last week. I was out visiting some sites, and there was a dual axis tracker system that we didn't get to make it to, and so that would have been interesting. But it was looking at the images, it looked like the ground coverage ratio was lower just because of the added shading that's happening in those wintertime months, especially.
Yeah.
Awesome. Thank you for answering those final questions. And as mentioned at the beginning of this presentation, what was covered in this talk just scratches the surface of the amazing course that Randy and Ryan are going to be co-facilitating starting May 3rd. and it's going to be hosted on HeatSpring about Megawatt Design. So Ryan, if you want to give a quick synopsis to people who might.
Yeah. So this is a class we've been doing for a while now, and it's Randy and I are co-teaching it, and it's really designed, it's geared towards systems, sub 5 megawatts, I would say, and really focus in on ground mount and rooftop systems, kind of running the complete, looking at systems, from early in design and all the way through commissioning, and kind of just there's a number of things that we talk about and going through and giving people, tips and tricks, things that we've learned over the years. And so it's been a lot of fun. We've had really good enrollment, really good participation in the past few sessions, and so it's definitely something that we've gotten great feedback on. Randy, I don't know if you wanted to.
Yeah, I'll add a little bit more, which is that it is geared towards folks with experience. Kind of somebody, if you got the equivalent of kind of a NABCEP certification, you know how to design PV systems. It's focusing on especially residential, small commercial. Scaling that up, applying it to larger scale projects, both behind the meter and front of the meter. And we spent a lot of time focused on, kind of the value engineering part of it, decision making around the designs, and kind of the design process, and where you can, where it makes sense to add time, spend more time analyzing some of your options, like the stuff we were talking about today: ground coverage ratio, loading ratio, equipment selection, and how some of the but we also do cover code, because code has a large impact on a lot of those decisions. Yeah.
Awesome. And thank you for plugging that. Just a reminder, that starts May 3rd. And we have our 2021 Solar Plus Storage Workshop Series, which Ryan and Justine Sanchez, who's not on today's call, are leading the way for these workshops. Ryan, do you want to give a quick plug for that too?
Yeah, so this is, Justine's doing just a ton of work on energy storage, and so we have the NFP codes class out now. We'll have the A55 and fire code stuff out very, very shortly, tail end of that. And so HeatSpring again is the place to do that. And then we're also doing in-person individual company type presentations for those that are interested in that.
Awesome, thank you so much. And the links for both the HeatSpring courses are in the Zoom chat, so please refer to that to sign up. And our next AMA next month will be with Energy Toolbase. We will be announcing the topic and the details to register for that in the post AMA follow-up email, so keep your eyes peeled for that. Thank you so much for attending this month's AMA. Thank you so much to Randy Batchelor and the folks at Soul Rebel for participating in this really engaging discussion. And thank you everyone for your really amazing statements and questions for our panelists. Randy, do you have any other concluding remarks?
No, yeah, this was really fun. It was really helpful. We didn't get to talk about the super high 2.0 loading ratios, but I'll have to sneak peek is that that connects in with your storage, and hopefully you can talk about that in some of your storage classes.
We can wrap that into a storage conversation and how we can make that happen. That's a good idea.
Yeah, but that's where we're seeing those really high loading ratios with DC coupled storage in some markets, and where you can do clipping recapture with the DC coupled storage. That's a really interesting topic, but obviously not one for today.
We'll just have to have you back on another time. Well, thank you so much, everyone, for joining our Ask Mayfield Anything session today, and stay in touch with us. Join our newsletter, and visit our website, mayfield.energy. Thank you, and we'll see you next time. Bye,
Thanks for your time, everyone. Bye. Thanks.